Morning, everyone. And first off, thanks everyone for joining this particular talk. My name is Mingmin. I have Xinli with me to co-present this talk. And today we will be talking about fast copy on write with Apache Parquet. Cool. So first, just want to talk a little bit about myself. My name is Mingmin. Currently, I'm leading one sub-org under data infrastructure team. I'm managing the real-time data and search platform team. And Xinli is a senior manager managing Kafka team at Uber. And he's also a Apache Parquet PMC chair and Presto committer. Cool. And here's the agenda that we have for today's talk. So we will first cover briefly about Uber's data infrastructure architecture. And we will talk about some of the challenges that we face for this upsert particular problem. And then we will dive into the introduction to Apache Parquet, and we will talk about our solutions for this fast copy on write with Parquet. And at the end, we will conclude with the future work. And all right, so let's move on to the Uber's data infrastructure architecture. So at Uber, movement is what we power, right? We are moving things, we're moving people, we're moving food, right? You can order a ride sharing services. You can order food, right? And then under the hood, there are a very big data platform services that are powering the whole business, right? You think about it this way: when you order a Uber ride, under hood, you were able to see, the ETAs for your ride. You was able to see the fare estimation, right, for your ride, and all of this under the hood is being powered by the data platform, right? And as you can see in this diagram, on the bottom left, right, there are various data sources, data that will be ingested into the data stack, right? There are basically online data storage, databases, and then the change log will be captured and ingested to the data lake. There are mobile events, various data's, telemetries, application logs. Those will be ingested, right, to Kafka, and then further routed to our data lake via our ingestion services, right? And we are actually heavily using Hudi to write to the data lake. And we are also using cloud object storage, HDFS on-prem to store the data in the storage layer. And we have, afterwards, we have data modeling, data warehouse to further process those data, right? And on top of that, on the left-hand side, you can see we are using various open source technologies. For example, Flink is heavily used for real-time processing, streaming processing, and we are also using Pinot. Pinot is another open source technologies that are heavily used for OLAP. And on the right-hand side, as you can see, we are using a lot of other open source technologies. For example, Hive for ETL, or we're using Spark right, for batch processing, and also Presto, right, for interactive queries. And on top of the analytics layer, we're building various BI tools, right? People can just write their query. They can set up the daily run for their query. They can set up their dashboard, which will show the trend for your data, right? And there's also workflow engines, data workflow engines. We are also heavily using open source technologies. For example, Airflow, which we built in our own in-house version. We call it Piper. There's also a UI front-end layer on top which people can drag and drop for creating their pipelines, right? Which is the UWalk in this data workflow box. And then there's also like metadata management, like we can people will be able to view their data set. They can create say an ingestion pipeline. They can create a Kafka topic, right, to ingest to the data lake. And all of this together is powering various use cases. People can create their dashboard, they can create their BI reports, right, and analytics. People can do real-time analytics, interactive analytics. And then machine learning, of course, is another big use cases on top of this data platform, right? And we are not only serving engineers within Uber, there are also data scientists, data analysts, right, who are also heavily using our data stack. Now, further zoom into the Lakehouse platform, right? So this is pretty much like the lower stack that we just briefly mentioned. So on the left-hand side, as you can see, we are ingesting various data, like from event streams, databases, change logs, mobile events, right? Those data, most of them will be ingested to our data lake, and we are storing it via Hudi table format. And that is basically the raw tables that you can see on the left-hand side. And then the raw tables is probably not necessarily what the end user really wants, right? They want to do further processing. They want to do further ETL pipelines on top of the raw data sets, right? So we are heavily using Spark, Hudi ETL to really further process those data into incrementally to get like the derived data sets, basically the modified table, as you can see on your right-hand side, which is also stored in Hudi format. And our end users will be using various tools, as we just described earlier, to run their jobs, to build their dashboard right on top of some of the raw data sets and then the derived data sets, right? And of course, machine learning, as we just mentioned earlier, is also one big use cases of the Lakehouse platform. Cool. Moving on to updates, right, in the Lakehouse. Think of it this way, like a data set is not necessarily it will be written for the first time, but it's likely going to need to be updated for various reasons, right? For example, like when you take an Uber ride, when you book a ride, you may put some tips, right, for your driver. But then after you finish your ride, you may change your mind. You may want to increase your tip, right? You may want to adjust it for whatever reason, right? And even if it's after like the trip is completed for some time, you can still like say change your payment method. You can change your payment profile, right? So those things can change afterwards, right? We need to be able to update the data set in some way. Also, there are like online database change logs, change data captures that are written to the data lake, and in some cases, like the databases, there are changes, and we also need to update the data set accordingly. Last but not least, we also need to change data for some compliance reasons, GDPR. Or redactor, for example, like for some kind of the compliance requirements, we need to change or delete or hide some of the data, right? So those also need to be the data set need to be updated as well. And updating those data sets is not that easy, right? It's not like you can change certain fields, easy. Because for one, the underlying storage system we are usually using append-only storage system, right? So if you need to update the data set, in some cases, you need to make a copy and update in the new file, and then change your metadata to point to the new file. And then, some data, right? For example, we are heavily using Parquet to store our data, and Parquet also come with compression. And when you want to change your data, when you want to update your data with compression, it's not that trivial, right? You want to decompress and update, right? Lastly, it's not, to locate the affected data, sometimes it's not that trivial. We may need some sophisticated technologies to locate the data files that need to be updated, and sometimes it's pretty slow, right? So further zoom into the Lakehouse data stack. So first, we need to store the data. Usually, we are using various, format. Parquet is one of the most commonly used file format to store our data files. You can, of course, use some other format, for example, ORC, right, which is also very popular in the past. And those data files will be stored for our table's content, right? And on top of that, which is the metadata, right? These are the information about your table. This could be like the table schema, right? Partition file, and some other information about your table, right? In the traditional Hive dataset case, metadata is stored in the Hive metastore, right? And then when the table format emerges, like for example, Hudi, Iceberg, Delta Lake, right? There are additional metadata, being created on top, right? They keep their own metadata files in this case. And on the right-hand side, there's also index files that's needed for efficiently locate the data that we need to, the data and the record within the table, right? And in the, some popular like table format, for example, Hudi, there's various indexes, for example, bring filter, stats indexes, right, which are used to locate the record efficiently. Now, let's dive into a particular example that we want to update a table, right, or we want to update a data set, right? Think of like this particular example that after a trip complete, right, we want to update the tips, right? You met a really nice driver, you want to increase your tip, right? And the table was already written and ingested to data lake. You want to update this particular field, the tips field, right, with the new value in this case. And then there are various challenges that we can see, but I will hand it over to Shinli to talk about how updates are being handled in different cases.
I have this. This one. Yeah. All right. Thanks, Ming, for all the preliminary introduction about the use cases, about the updates, about the logical view of the table updates. So it make my talk easier to explain later. So your previous slide, you see the logical view of the table. You want to update from the tips from $3 to $5 because the drivers are really nice. You want to really appreciate him. Now, so in the next few slides, I'm going to walk you through how the update process looks like in different table format, particularly before the modern table format like Iceberg, Hudi, and Delta Lake emerges. People generally use the plain Hive table. So how that looks like, how the process of updating looks like. And then I will walk you through with the modern table format for like Iceberg, Hudi, etc. for the updates like copy and write, merge and read, how essentially the file is read read how the updates get into that file. And then after that, I will point out, hey, even with the table format, the copy and write could be challenging for some large-scale use cases. And then that's why we introduce this fast copy and write in Parquet and showcase how that from the technology wide, how we solve this tough problem, how they help our use cases. For instance, like the compliance, like right to be forgotten. In the end, I will talk about the use cases and the limitations of these solutions. For these slides, I'm going to show you before the modern table formats that show up. People generally use their plain have table. What it does means is use, for instance, the HMS for storing the metadata, and then you can use the storage system like HDFS or the GCS S3 to store the data. So I just write down the updates. It's actually the pseudo SQL updates. Updates the trips tips from to the $5. Let's update where the trip UUID you want locate that particular record in the table with the trip UUID equal 3, 4. Well, this is a table. Earlier we used like a 1, 1, 1, 2, 2. That's make sure that's a fake. This is also fake. 3, 3, 4, 5. It's just it's a table in this slide. And then the data store that day happens because the table generally partitioned by a date. So the date particularly refers to a partition. In this case, on the diagram, on the left diagram, you can see we have 3 partitions: partition 1, partition 2, and partition 3. So in the data store, 2023 June 30, I mean the partition 3. That is the data that was stored for this trip UUID. Let's walk through on the left side the diagram. So we have metadata and data. As I said, the HMS can be used as the metadata, which is store, for instance, the table location. Where is your file located for this table in your storage? And then under the table, there's different partitions, and each partition can be stored in the different location. Then the storage location is part of the metadata. So when the reader read this HMS and know that this partition pointing to the HDFS location, for instance, partition 1 has the content data file, which is the Parquet file 1, Parquet file 2, all the way Parquet file n, and so on. So partition 2, partition 3 is just laid out like this. Now, let's walk through that. When you try to update a field of the tips to $5, how can we do that? So first of all, the signal that we get from this update SQL statement is data store, which is 23 June 30, which is partition 3. So that gives us signal that partition 1 and partition 2 is out of the picture. So we just look at the partition 3. But no other signals to tell us which file or which Parquet file has that trip. So we have to read the whole partition. You can use Spark, maybe on the Yarn, on the Kubernetes, read them into memory, and then look up that one by one that which trip have equal this trip UUID. And then once you get there, and you just update that in memory to $5 and write to disk, right? So at the end, so we walk through the step 1, step 2, step 3, read them into file, update, write to disk. Eventually, we generate a whole bunch of whole new Parquet files. So we store them in the different locations. We call it partition 3 underscore new locations, maybe on the HDFS or GCS, whatever. And then you go back to update the HMS and let it pointing to the new locations, right? And then you cut the pointer of the old pointers of the old partition 3 locations. Now the reader start reading from HMS and know that, hey, this is a new location and get the new file. Then the tips is $5, not $3. So we finish this update process, but you can see you have to read the whole partition data, which is quite a lot. For some large tables, it could be like a terabyte data, even for one partition. Remember, one partition is 1 day data, right? For large user cases, that's quite a lot. So let's walk through the modern table formats like Iceberg, Hudi, etc. The idea actually applies generically to all three, including Delta Lake. On the left side, it's still the metadata and data. When you start with the catalog, it just points you to the table location. Then you go to that storage table location. Under that directory, there are a bunch of metadata files that will tell you a lot of things about this table. For instance, schema. Also, the partition locations. Right? This is the same. Partition location is pretty much the same to the plain have tables. Now, when you go to that partition directory or subdirectory, that's another bunch of the metadata or manifest files. So that will tell you a lot of things about this partition. For instance, snapshot. So all the modern data tables, they use version snapshot to do the ACID transactions. For instance, when you update, every update will bump up the version, generates a new snapshot. A snapshot is a set of the files considered to that current state of that data. So in the left side, I use a green box to show one snapshot. For instance, this snapshot includes the files Parquet1, Parquet2, all the way Parquet n-1. And then the so on, so the partition 2, partition 3. Now, when you apply the updates, the same signal, right, the data store we know is a partition 3. Now, in the like Iceberg, they have quite a lot of useful metadata files like index to help you to locate it, that inside this partition, which Parquet files have the piece of data that you want to change. For instance, statistics. Statistics is a set of a min-max. Essentially, it forms a range of data. When the data, the change data to be outside of this range, you know that the file doesn't have the data you want. You can just skip. So make this very, very fast. Now, on the copy on right, once we located, hey, the Parquet file 1 have the data we want to change, so they will just touch the Parquet file 1 and read it and change it and write a new file called Parquet new file 1, and then they will update their snapshot manifest file. That will bump up the version and include this new file and exclude the old file. When the reader reads this, they start reading this manifest of this snapshot and know that Parquet 1 is out of the picture, but Parquet 1 new Parquet is inside the picture. So they get $5 instead of $3. So you can see that it's a great improvement comparing with a plain have table that you don't need to read the whole partition. You only need the files that need to be changed. Now, there's another updated mode called merge on read. All the updates, the layout, all the same. Only difference here is when you do the updates, you are not so eagerly to create a new file. Instead, you put a Delta file into that directory, and then you just add association in the metadata to let the reader know that when you read this file, there is a Delta file appended to it. You need to resolve it. For instance, the old file have 3 still there, but there's an update called 5. The reader will give the application that is $5 instead of $3. So the updates is quite simple because you only place the Delta files or change the Delta files, which is very, very small. But the drawback is the reader need to resolve the changes. So this is a very simple comparison of copy on write and merge on read. Simply speaking, copy on write is at the writing time, you create a new Parquet files, and merge on read, you just place the Delta files, and then copy on write may increase the storage usage, but not much concern for that. It's slower for write, but it's faster for read. But merging on read is on the other side. So it's fast for write, but slower for read. So I have to point out that for some use cases, I mean, the two use cases can be used for your own use case by case, but some use cases for like compliance, like GDPR requires right to be forgotten, right? When, for instance, I have an account in your company, I request to delete my account. You have to physically delete in all the storage, all over the places, online storage, MySQL, offline, all the different tables. That's quite a lot of work. So because this is offline, you don't want to use a merge and read, right? So what's the sense of doing that, right? Copy and write generally is what we use. But because of large scale, the copy and write, even they have done the improvement on the modern table format, is still not efficient to accomplish some large scale use cases. So that's why we want to introduce the fast copy and write. So let me briefly talk about the Parquet. Parquet is a columnar data file format for the big data processing. It stores the complex data nested with a highly efficient and compressed manner. It is widely used by almost all over the places in the data analytics, right? Spark, Delta Lake, Iceberg, Parquet, almost everything on Parquet. So the structure I just laid out on the right side with a footer, because it's a column storage, it divided into different row groups. So each row group is a full view of the whole table. So each column has the data inside the row group called column chunk. So the column chunk is further divided into pages. So page is a unit for I/O for the encoding, compression, even the encryption. Before we introduce the fast copy and write, I want to introduce called the row-level secondary index. So index is to help the updates to precisely or quickly locate which Parquet file is having the data that you want to change. So different index may give you different precisions. For instance, the min-max, the statistic give you very coarse grain. You may have a lot of false positives. For instance, in Hudi, we built up called the record index. So you give a key like a triple UUID is a key, and value is a file location or file name. Right? So that is a much improvement, but still not efficient. We want to introduce a row-level index, which means you can look at in the middle of the table. So the key is still the like a triple UUID. You can use whatever actually the data that you want to change. Basically, the row is a row key. And then the value, not in addition to the file location, file name, we also have this structure information inside the Parquet called row ID. So this information can help us for the fast copy and write. Let me introduce the fast copy and write in Parquet. So by the way, I want to make clarify that because copy and write is quite common in the modern table format, like Iceberg table, Iceberg, Hudi, etc. The question is, are you guys introducing Parquet a new copy and write? Short answer is absolutely no, because Parquet is a file format. Like Hudi, Iceberg, Delta Lake, they are the table format. They are in the different positions. They are not competitors. But there's something we can do, for instance, we are talking about here, is to improve the copy and write process by speed it up. Speed it up like very fast, sometimes kind of like 5 times, 10 times faster. So, the brief idea is inside this Parquet file, because the copy and write essentially is you read old files and on top of that you apply the updates, generate a new files. So this process is treated as a black box. We can speed it up. So this is how the overall idea of the copy and write with Apache Parquet. With the row level index, we can accurately locate which Parquet files, not only that file name, but also inside the Parquet, the row, the page, the row group, etc. We have that information. So only decoding, decompressing those pages that need to be updated. For instance, you only have 1% of the data inside the Parquet file need to be updated. There's a lot of pages you don't need to decoding, decompression. That's the most time-consuming part of the copy and write. So you can imagine that will increase the speed a lot. For the remaining the pages that you don't need to touch, it's just bed buffer copy from disk to disk. That's how you speed up the. Well, the slide doesn't look nice. It just. Okay, so here, looks like we run timeout. Here, I just shows in the Hudi how use copy and write within Apache Parquet. On the left side, traditionally without this technology, how it works. First, you receive the updates from the request, and you look up the index. So here I can use the file level, basically called the record index, right? So it give you where is the file. That's it. And then you clone the new files and apply the updates. Basically, you have to do every record by record, decryption, decompress, decoding, etc., and apply it back. And then you update the snapshot. That's it. Now with this new idea, we still generate the new files, but from the old file to the new file, the speed is increased. So this slide just gives you the idea. We are not fundamentally changing the copy and write process, but instead we want to increase the speed. How it works? In the previous slides I show on the right side is called copy and updates. So what is a copy and update essentially means? So traditionally, when you have a Parquet page, what you need to do is on this page, you can do the decryption, decompression, decoding, record disassembly. In the Parquet, there's a lot of repetition level, definition level, etc. And then you apply the updates, and then reverse it back all the way to write to the new files. Now, with this fast copy and write, you can just rewrite it by skipping for all the pages in the gray box. I just show that for all the pages that it doesn't have your data, because we have the row level index, right? We know which pages have your data to be changed. Now, for the data not changed, just grayed it out. We don't need to do anything, just literally bed buffer copy. And then for the pages that you need to change, you just read it into memory and write to the new pages. That's how it can speed up the overall copy and write process. So limitations is because we have to build up the row level index. That's quite a lot of information comparing with the traditional index. The storage size of the index is very large. So that's why we keep it separate storage, like outside this table. And second, how do we make sure that when the original table updates, how do you update the secondary index in sync? Because you keep it separate. The solution could be integrated with the table format. Conclusion, I just want to summarize what we talk about. Efficient upsert are critical for the data lakehouse. The speed remains still a challenge when the volume scale up. Faster copy and write within Parquet with row level index. We can skip the unnecessary data pages, read and write efficiently, and improve the speed of the upsert. Yeah, so the future work basically is the limitation that I just show you how to improve the size, integrates with the table format.